from Redpine Signals, and the title of his talk is Accelerating AI Applications in Hardware. A brief bio of the speaker. Mr. Anand Joshi is Senior Director of AI Products at Redpine Signals. He has over 20 years of experience in semiconductor and embedded industry. Prior to joining Redpine, he was market analyst at Tractica with focus on AI. He advised many Fortune 500 companies regarding AI products and strategy in that role. Earlier, he was Vice President and General Manager of a business unit at Alton Calsoft, which was Adobe's scaling partner and specialized in Adobe Flash Player. During his tenure at Calsoft, Joshi started the business unit and grew it to over 100 people worldwide. Anand was also a co-founder of Poseidon Design Systems, a startup focused on hardware acceleration of video, where he successfully raised 2 rounds of capital. His early career spanned various engineering and marketing positions at Synopsys and LSI Logic. Anand has MBA from University of California, Irvine, and MSEE from Virginia Tech. So, over to you, Anand.
Thank you. First of all, thanks to IIT for having me, and thank you all for attending this session. I got a few slides here, actually a slide deck, on accelerating AI algorithms in hardware. And how many of you here have understanding of AI or just curious about this topic? If you could raise your hands. Okay, so few. So I'll spend more time on giving you the basics of AI rather than the acceleration part. There are 2 parts to the presentation. First one is about the AI, the complexity, and the second part is how do you accelerate it. So what do you see? Are you a psychic? You see a beautiful child here. You know, my 6-year-old will probably go, oh, so beautiful. But AI sees something else. This is what AI sees. When you input an image into an algorithm and you run that algorithm, you get a percentage, a classifier, which tells you the chances that this particular child is going to have certain disease. And there is a company called Face2Gene that does that. And if you go to their website and read the testimonials, it's almost very emotional. There is this mother thanking this company because it discovered, the child was not behaving correctly. And this particular software detected that she had 59% chance of autism, so when they went and did those tests. There is another guy who was, having suffering for 15 some years. Doctor tried all kinds of tests, they could not diagnose him. Eventually, he went to this website, and they found out he's likely to have some disease. So really, the way your face looks, every feature of your face has some correlation with the genes. And that genes essentially is correlated to disease. So by correlating all of these things together, you can find out, what is the chance that you'll have certain type of disease. So there are things like this that are giving a huge boost to artificial intelligence in general. Here's another example. This particular paper is out of MIT, and what they are doing is they are collecting a sample of vibrations on that piece of paper. And they're essentially using the algorithms, and they record the sound from the vibration that you see. And now you are suddenly placing a microphone in a camera in a room by using your camera, and they're able to record this sound. And so other very fascinating things what you can do with AI. And these are the type of things that are giving rise to AI, and this is really the cool technology of this century. So let's spend a few minutes talking about AI. So AI is nothing new. It's been around since 1950. Machine learning is really the subset of AI, and deep learning is even a smaller subset of machine learning. And then within deep learning, you have what is called as neural networks. And that's really the hot technology as of today. Everybody is looking at neural networks to solve their problems. And it does have numerous applications that you'll see in the future. The neural network essentially is a set of connected nodes, if you will, and where you're performing mathematical operation. So in this case, your data is input to a model, and you are generating some results based on that. So here is an example. If you want to detect that image is either flower and elephant, you would create some sort of neural network, and you will train that to recognize whether it's a flower or elephant. So that part is called as training. And then on the other side, when you take new data, so you take a new image and you feed into that network, it predicts that it's a flower. So any neural network has 2 parts, training versus inference. And so when it comes to taking this into hardware and accelerating it, you have to keep these 2 things in mind. And this is really an example of how that neural network might look like at a node level. So here you have input nodes and some hidden nodes and some output nodes, and you're running all kinds of computations. Here there is another example how you would use neural networks to detect an image. So this particular, I think I just went past too many. This particular network is called as convolutional neural network. What you are doing is you are taking a small window and you are essentially sliding it across the input image. And within that window, you have multiple parameters where you are trying to capture certain features. And you are doing it multiple times. And you are doing convolution. That's the basic mathematical operation. And at the end, you are creating a set of, a one-dimensional matrix, if you will, which is going to tell you the chances that this particular image belongs to a certain class. And so this is just one of the many neural networks that are out there, and there are hundreds of them. They actually call it neural network zoo. There is feed forward, there is recurrent, there is LSTM, all kinds of things. And because the complexity of each one varies, there is a lot of operations that are being done. You need a hardware to accelerate that. And how do you, before we go and take a look at the actual capacity that you might need to accelerate, let's take a look at an example here. Because this is an example in which you are trying to read an image and trying to generate a statement that tells you what's in that image. So you would take an image, something like this, and you would input to what is known as the neural network. In this case, RNN is what they're using. And then output would be the text that does that. When taking an AI algorithm and mapping it to hardware, there are a lot of stages in addition to just the neural network. And here is an example of what you might go through. So when an image comes into a system, you have to do some pre-processing. You might have different light conditions, you might have objects blocking, you might have unwanted things. So you almost go through the first step is your pre-processing, in which you are doing noise reduction, scaling, color space conversion. Maybe you are better off doing black and white rather than color. The next step is selecting areas of interest. So in this particular example, you might find that people are interesting, vegetables are interesting, the people are walking around, there is some dust here. So these are the areas of interest that you would essentially try to identify. And then from there, there is something called as feature extraction. So you might try to label that this is one feature. You might do some pre-processing, so you might be able to identify some objects readily without even having to go into a neural network. And then, after all this is done, you're actually going into the neural network phase. And so this whole pipeline is what makes an application. And it's at every step, you need lots and lots and lots of compute power. This is a chart of how many flops you need to process an image. And these are some of the popular neural networks that have evolved over the years. So this is, the traditional ones, GoogleNet and ResNet, and then some of the newer ones here. And if you see, the gigaops increases from, up to 40 gigaops to recognize a top one image. So top one is basically your class. Whatever you're using to predict has to match the correct class. Now, this particular example was run on ImageNet. So ImageNet generally has average 256 by 256 standard. The size vary, but you can assume that 256 by 256 is approximately the size of your input image. And you need, let's take an example here, Inception, that seems to be giving the best result, and take number 20. So you need 20 gigaops to process one image that's 256 by 256. As soon as you start adding the real life scenario, the complexity that shoots up. So this is a very simplified, sort of table in which I'm trying to come up with some estimates. So the 256 by 250, let's say that you need 20 gigaops. Now you're inputting 1080p image, so that's going 30 times bigger than that. The current most popular image resolution is around 4K, so you're looking at 2.5 tops. Then we have video, which is 30 frames per second, so now you're up to 75 tops. 60 frames per second, which is really what you use in a TV broadcast, you're looking at 150 tops. To give you a comparison, the state-of-the-art Xeon can only go to 5 teraflops. So naturally, this is a huge compute demand on a typical PC-like system, or even high-performance computing, which is why there is a new class of chipsets and hardware that's emerging, which is specifically addressed to solve the AI acceleration problem. And so how far, this thing can go because AI as such is very compute intensive. And this is a slide from Oak Ridge National Laboratory. They are one of the top research institutions in US, and every few years they publish their roadmap and what are their needs for scientific computing. So scientific computing is all about, weather prediction, thermodynamic analysis, or genome, genomic prediction, things like that. So this was published in 2012. And if you notice here, they are saying that they need around 20 picoflops. This is again for a supercomputer, which eventually, typically boils down to your day-to-day needs. And at 2017, they need 100 to 200 picoflops. So we are petaflop. We are nowhere there that capacity, even with the highest commercially available AI workstation that you would need. In a supercomputing environment, you could probably go there, but this increase here, 5 to 10 petabytes of data, which 5 terabytes of the bandwidth is just mind-boggling. I mean, even today, we are not quite there. Pretty soon we'll get there, and this is just going to get more and more complicated. However, from an AI application point of view, there are different needs for different applications. And so roughly, you can segment an AI application in two parts. One part is the enterprise and data center, where you are dealing with a tremendous volume of data, a lot of audio, video, image, text, stored data, and you can go into terabytes or even petabytes. On the other side, you're looking at embedded devices where you're trying to do things on the fly. So smart camera, for example. Smart camera will take, you can install it in a crowded intersection, and it will do things like facial recognition. Or you could install it in a retail store, and it will tell you that, okay, 50 people went and stopped at this particular shopping counter. These things will be done on the camera itself. Drones, obviously, you know about them. They do all kinds of things, following a person or a vehicle, the object avoidance, so on and so forth. So all of these devices here, consumer cameras. So there are cameras. You can put them in your on your door, and they should send you a picture of the person who's there, and the person is not identified. They look it up. They try to match it with your contacts, even if it's not there. There might be a thief. Maybe they'll look, go connect with police database. So they can raise alert, things like that. So a lot of these things are actually done on the device itself. What you do on the server is that you need a connected network connection. You have to send data there. You do the calculation, and you send the results back. And the applications on the enterprise and data center side tend to be heavily focused on compute, storage, and network. Whereas on the embedded devices side, the applications tend to be focused more on result-oriented, where you have to have result within certain given time. Automotive is another big thing. Cars are going to be self-driving, which is everybody's dream. But there is a lot of AI happening inside that car. Robots, pretty soon robots will be able to find their path, and you might even have consumer robots. So each one of them, if you categorize, there is the needs. So you can actually go at around 1 teraflop, but it has to run within that chip, within a given power budget. Whereas here, you need as many flops or ops as possible. And so with that, let's go deep into the AI hardware and what's happening there. So this particular picture is of a robot that's delivering pizza. It's also already operational in United States, and this poor chap is wondering what's going on because the robot is finding its way. This is a typical compute environment. You have storage, network, and of course a big compute system here. Your data might be coming from a network, which might be hopping with 1 hop, 2 hop, or hundreds of hops. It might be coming into your local storage, which might be a flash or might be a hard disk-based storage for long term. And then you have this whole slew of things that are happening within your server. So the data comes within here. It might go on a local storage, mostly flash these days. Then there is the RAM, and there is the cache. So everywhere, you have to make decisions when you are trying to run AI application. And then within CPU, GPU is the most popular choice today for hardware. So you might have a host CPU, which actually brings the data in, which gets passed on to GPU. You do the compute, and then you go back. So the system itself is very complicated. And unfortunately, the world is focusing today only on the compute part, not on the rest of the part. So There are a lot of solutions available here, but there is hardly anything, even in academia, that talks about how the impact of particular algorithm on overall AI application performance will be. So these are the different options available. So you could start with a CPU. So CPU has traditionally fetch, decode, and execute type architecture. So you bring the data in, you do operations, and you execute, you store it back. Unfortunately, most of the AI algorithms are very pipeline parallel algorithm, and there is a lot more competition going on. So that usually does not work well for AI. Then you could actually have multi-core CPUs or some small DSP engines. You got some level of parallelism, but again, it doesn't usually work very well for AI. GPUs seem to have appeared as the best option at the moment to run or accelerate AI applications. And I got a slide on GPU. We will talk more about this. FPGAs, which is essentially a hardware synthesis of an algorithm, are appearing to be the next prominent option. But again, there are lots of pros and cons around there. And ASICs are something that's specifically designed to accelerate these algorithms. So ASICs seem to be the most promising of all the things. And the accelerator is something that's just started appearing, where you are just taking parts of algorithm, moving it into something called as coprocessor type architecture, and trying to generate the meaningful results in meaningful amount of time. So on the left here, you have programmability. On the right side, you're losing that. It's more application specific. CPUs, they've been around for 20 some years, so it's very easy to get hold of them and run algorithms. The performance typically tends to be low on this side. Power is high, whereas there, you have high performance, and you can also optimize for power. One thing to keep in mind for interface and training is that depending on the choice of hardware, you are losing programmability, and you are losing suitability for one or the other architecture. So this is, most of the server class CPUs are very well suited for training. They could also be used for inference. So could ASICs and GPU. But the FPGAs and accelerators are primarily for inference part, and they're not used for training as such. So this is the big picture in terms of the chipset options that are available to accelerate an algorithm and where things stand as far as industry is concerned today. So here you have different architectures, and here you have different characteristics. So the needs of applications in the chart I just showed you, you might want a low power and high performance, or you might want high performance and power is does not matter. And then you might have different usage needs. So you might want them for training or inference, or you might want them for both. And then these needs will have to be mapped to the hardware architecture. So there is CPU, there is GPU, FPGA, ASICs. And then the others is really the what is called as neuromorphic, which is the analog way of doing computing. It's nowhere in the picture just yet, at least on the practical usage side. And true ASIC is really the pure hardware block in which you synthesize everything and run it through the systems. Again, that's not anywhere in the horizon as yet. So the red here is something where there are not enough solutions available. Green is where everybody is focusing on, and yellow is where the solutions are starting to emerge. So this is how, when you overlay your use cases, it will look. So on this side, you have ultra low power applications, such as IoT or sensor fusion. You are trying to do things on the device itself. And then as you go to the right, you have big data and server class chipset in which you are actually sending data via cloud to a very high powered device, and you are doing computation there. In between, they have this different class of devices. So mobile phones, we just started seeing some accelerators being embedded. Huawei just announced one. Qualcomm actually has some solutions. So we are starting to see some applications emerge, some hardware emerge around the mobile phones. How it will be used, what are the use cases, it's still uncertain. Nobody knows how that's going to evolve, but we'll have to wait and see. In between, we have something like smart camera or drones or other embedded devices where you have a little more power available. You might want a little more compute capacity. And automotives are in the class of their own. you have a decent amount of power available through your LED battery. And you can do a lot of things within automotive, so you might want decent performance also. So there is a separate chipset class for automotives. And then this is a whole open field right now dominated by Intel and AMD and such, where you have to have as much compute as available. So this is a typical compute requirement. So one thing to note here is that I mentioned here I mentioned tops and here is flops. So because AI is such a fragmented world with a large number of applications, people have tried all kinds of different things on compute. Some use floating point, some use integer arithmetic, some use fixed points, and everybody thinks they are the best. NVIDIA actually introduced something called as TensorFlop, which is a 4x4 multiplication that works best with CNNs. Nobody knows how that will work for 3x3 multiplication or 5x5. What happens when you go 5x5? You're losing because you're essentially not utilizing the hardware. So there are a lot of considerations in how you might want to measure the performance. But this is the general sense. You have a chipset here. This is from a company called Movidius. That's part of Intel. They make ultra low power chipsets that go around 1 teraops per second. Then some in between, this is a company called Mobileye, again part of Intel now, and Xavier is NVIDIA. So they make chipset for automotive, and again, this goes back to my previous slide in which I'm saying that you need mid-level performance. And this 120 TensorFlops is state-of-the-art from NVIDIA, which is being used in their DGX-1 workstation, which is really the most powerful AI computer available today. And in terms of power, again, you have a range starting from 0.25 watts to 30 watts. So a lot of these ultra low power devices, wearables and sensor fusion, you have to have something below 0.25 watt. Again, that's very hard to achieve, very complicated to implement. There are a lot of considerations that come into picture when you're optimizing for power. You might be able to do away with less than 2 watts in mobile phones and tablet-like devices. You could go up to 30 watts in automotive. I haven't seen too many products going beyond that. And then beyond 30 watt is mostly your PC and servers domain. So there is a lot of scope for high power there, but performance is extremely important. So I'm going to spend some time talking about these different classes of devices and just give you some trade-offs. So CPU, roughly we can again classify into 2 classes, embedded and enterprise or data center. So Intel has the best solution. Xeon is their chip, which is targeted towards data center market. Now Xeon actually has few very interesting things going on. There are 3 segments within Xeon product line. In one segment is just a traditional CPU architecture with lots and lots of cores, and you can spread your algorithm within those cores. Then the next class, they're actually integrating FPGA within the same chip. So you have to have an engine which actually accelerates the algorithm in FPGA. And the one level above that is a ASIC in the same core. So now you need another piece of software to take your algorithm and map it to that ASIC. And Intel's approach is that everything sits on one CPU or one die. You buy the SoC from them, it's got everything. And that goes against the approach that other people are taking, in which they're actually putting accelerator into the system via PCI Express interface or some NVLink or other interface. On the embedded side, since you are very constrained, you must be very good at doing the algorithms that you do. So let's say you have a camera and you have to do face detection. You must do a really good job of detecting the face because that must be optimized for the architecture that you're given. And of course, libraries play important part. So many vendors actually have to have their own algorithms implemented in the chipset that work best. And this neural network engines is actually, turning out to be the hot things within all the embedded chipsets. What it does that it only accelerates the algorithm where you are consuming a lot of power. So it's a block that you drop into the system, and suddenly your chipset, which was based on ARM, becomes an AI chipset. So ARM is really the only player in the embedded world. MIPS used to be there, but they are going down. And this is a very fragmented space. Lot of startups have appeared here. They're all trying to do different things, and we don't have any winner, or or even a trend as such that this particular algorithm will run for this application and will give the best results. On the enterprise class CPUs, Intel actually is the only player right now. AMD doesn't do much. Their chipsets are primarily for consumer class of devices. And the power is as high as 200 watt per SoC. So if you have 8 of those, you have 1600 watts and you're essentially smoking the building. Intel is the best choice for inference. So all these engines, Alexa and Siri, they actually run on Intel. They don't really need anything GPU. And if you have a simple neural networks, low end, what I call, you can get away by having a powerful CPU. So again, because Intel has been there and everybody is familiar with it, they are being used frequently to train as well as infer AI applications. The next set is GPU, and this is really the de facto standard for AI algorithms. Any AI tool that you see must work on NVIDIA. Otherwise, it's really not a solution. So NVIDIA started the general purpose GPUs, back in the days when Andrew Ng was doing PhD at Stanford. He was one of the first people who actually figured out how to use GPUs to accelerate AI algorithm. And that's really when NVIDIA's GPUs became prominent. They could not use AMD. But after that, NVIDIA realized that, well, there is a demand for this. And the latest Volta supposedly cost them $3 billion and 2,000 people. So they have invested a big time into this. And apparently the revenue has gone from 0 to $1.1 billion for data center market. So clearly they are selling a lot of these chips also. So there is a AI application server called as DGX-1B, which is the state-of-the-art AI server, if you will, that has 8 V100 chips, each one running 120 teraflops. So you almost get one, petaflops, one peta tensor flops operation, which is huge by any standards. Intel cannot even go beyond 20 teraflops, so it's a huge jump in terms of performance what you can do. Of course, it takes a lot of power, so each card is around 250 watt. So if you have a server, you need 3200 watts, and again, if a server rack is typically capable of giving you 10 kilowatts. So if you put 2 of these, rest have to stay empty because you're putting too much strain. On the embedded class, the TX1, TX2, and Xaviers are the GPUs that are meant for automotive market, although I've seen them used in other applications also. The power consumption is around 7.5 to 30 watts. So again, in a car, you're probably okay. And the upcoming architecture, Xavier, has got 30 tops. So notice that NVIDIA has optimized for tops here, whereas here they optimize for tensor flops. So clearly they view these two spaces very differently. In one case, they are thinking that people will do integer operations. In the other case, they are thinking that they will do, floating point operations, more matrix applications. So there are other companies also trying to compete in this space because everybody's noticed that there is a hot demand like hotcake for these. So on the embedded side, Qualcomm Adreno and ARM Mali are the two prominent names. Both of them have published libraries in which you can accelerate AI algorithm. And AMD Vega is a new GPU which is coming out in the market. It's actually already out in the market. That supposedly is expected to put a fight with NVIDIA. And the approach that AMD has taken is that they have open sourced everything. So you can go to their website, download, and you can build your own tools, whereas NVIDIA has everything proprietary. FPGAs are really hardware blocks in which you take an algorithm and synthesize and run it with your CPU. Again, the approach of Xilinx and Intel is what used to be Altera. Is different from what I just mentioned, that Intel's SoC approach. You need a accelerator card, and that accelerator card typically works with your host CPU, and it accelerates the algorithm. So Xilinx in particular is pushing this really hard in the data center market. They have not been very successful, but they're still continuing to invest. And of course, Intel Xeon, there is already the cards available with Altera FPGAs. And these are the two product names that are very prominent in AI product line for embedded. Again, the most of the usage of FPGAs is in the automotive side. And Microsoft is pushing it on the data center side. And they have developed an engine in which you can take an AI algorithm and map it to hardware just the way you would do with software. And that engine is supposed to be better than what even Xilinx has. So it's pretty big achievement on Intel's part. Otherwise, you have to essentially take that algorithm, do a synthesis, which is what hardware guys would do, and go through that whole verification process, which actually could take a lot of time and could be very cumbersome. And ASICs are the new kids on the block, if you will, the companies that are going specifically after AI market, and they're building chipsets that are optimized to run the AI algorithms. Most of them have focused on integer operations because neural networks don't necessarily have to have floating point. So most of the data path you will see in these chipsets is based on integer, although you can also run floating point at a reduced compute performance. There are 4 things that become important for the AI application when you're running AI algorithm. The first is, of course, the compute capacity, how many flops or ops you can do. Second is how many memory accesses you do, how many times you have to go outside and fetch the data and do the compute. The third is the P to P, so P is processing element, and because AI is so parallel, you have these multiple processing elements. How do you get the data from one element to other? So again, all these companies are optimizing their P to P communication, so all the P's are always busy. And then finally, scalability. How do you scale the system? So rather than having one chip, maybe you have 8 chips in parallel, or 64 or 128, and your performance just keeps scaling up. Again, as soon as you go beyond certain tera, ops or flops, the problem gets exponentially complex. But that is the sort of vision all these companies are promoting. And in last 3 years, over 60 companies have jumped in the market. So that's again, and the purse is open from VCs. So if any of you are looking to do a startup, this would be a good space to be doing it. There are companies like Nirvana, which is part of Intel now, Wave Systems and GraphCore. All of them have actually taped out their chip, and we should see some actual products based on their chipset this year. And on the embedded side, there is a company called Mystic who's building a chipset for computer vision applications on smart camera. We have a chipset that does IoT type applications on the edge. So there is a demo actually being shown. There is a company called ThinkEye who's doing chipsets for automotive. Again, a lot of different approaches. And they're meant for training as well as inference. So it can be used anywhere. But in general, these companies have a potential to disrupt the future. AI really is limited by the compute capacity and performance today. So the more ASIC companies pop up, the better it is for science to move forward. And so this is the performance today, the way I see it. CPUs are still at the bottom. FPGAs make it better. GPU makes it even better. And ASICs make it even better. And so this ASICs have just started to emerge. And it's going to be a very interesting ride for the next couple of years. And again, if you go back a couple of years, you'll see that all the activity is centered around here. And because AI is so new, sometimes I worry where things will go. So GTC is NVIDIA's yearly conference. It's, the thousands of users come and they talk about the latest and greatest architecture. And there is a big portion of that conference is actually devoted to academics. And there was no mention of AI computer vision in 2013. In 2014, Jensen, who's NVIDIA CEO, he talked about computer vision. Again, no mention of AI. But then suddenly AI came in the picture, and the NVIDIA created Pascal P100 around 2015. Then IBM and HP jumped in. And then NVIDIA created next version, and now everybody's in the picture. So now we have Amazon, Google, Microsoft, lots of startups. So it's only going to accelerate from now on. So that gives us lots of options on how you can accelerate your algorithm. But what's missing? Compute is not the solution. So the whole system picture that I just showed you, in which you're actually getting the data into the system, and your whole compute network and storage is running together. There is a huge set of problems to be solved there, how the actual application works and how you optimize your memory or network. For instance, is it best to cache the data on the chip, or you have some special cache architecture? What is the best protocol for the chip to communicate within the elements or within the network or even within the different cards? What is the optimal allocation of memory on different accelerator cards? Do you have more storage on your device or of the, I mean, it's all very much open and nobody really knows the solution to the problem. What the industry is doing is that they are just picking the fastest available option and putting it in there, and within a year or two, we will see some devices to start failing. Software infrastructure, again, it's very weak. How do you scale the system? How do you optimize it? How do you make the best out of hardware? There are some bits and pieces attempts here and there, but nothing concrete as such. The IP is another question. You build a hardware block. How do you best make sure that the application is utilizing it? Very, very few applications. The frameworks, TensorFlow. So if your chip reads only TensorFlow, it will not read Caffe. So now they're evolving a layer which is in between these networks and your hardware. So it's happening, but there is long ways to go. So with that, I'll leave you with this thought. I personally think that the hardware is the only thing that's stopping AI from going places today. The needs of AI are tremendous. Nobody really understands what happens in CNN and neural engines. Pretty soon we'll have this hardware. Then you'll be able to do experiments or training within a few minutes or a few tens of minutes, and you'll understand what's happening inside of that new NN, and then you'll figure out a new architecture. So once we get there, we are going to see many applications, scary applications emerge, to be honest. But let's just hope for the best and move forward. That's pretty much all I had. Any questions? So anything that accelerates an algorithm, you can call an accelerator. The CPU typically is a chip. So you know the motherboard, right? And then motherboard has its PCI sockets. So if you have a card that you plug into PCI socket, then in theory that's an accelerator, right? So you can have a system and you can plug the card through that PCI Express interface, and that will be an accelerator for any AI application. So NVIDIA or Xilinx, they make cards like that. You can also take the same accelerator and put it on a chip and do acceleration within that chip. So your CPU remains the same, but your data is passed to this engine via some memory, typical AMBA, typical bus I would use, or some custom interface. The accelerator is only doing the processing for AI, whereas your CPU is running the control part. So that's the difference between accelerator and a general, CPU. Correct. So ASIC is itself a programmable engine. So you can take any neural network, compile it, and run it on ASIC. Whereas for accelerator, you still have to compile it for CPU, and then that CPU will pass it to the accelerator. Correct. It does not do everything. I mean, you still have to compile it to the architecture, but CPU is taking the control. That's the difference. TPU? Sure. Well, so TPU is probably state of the art today, and their engine is also based on the integer operations. And when they started, they were around the performance where Pascal was. Of course, the GPU was in Kepler and Maxwell in those days. Now the latest architecture, V100, the Volta, is neck to neck with what TPU has. So TPU is being used by Google within their data centers. It only runs TensorFlow, and for a long time it was not even open to public. Now they are giving some limited access to public with their algorithms. So they have computer vision APIs via their website. You can use those APIs and they will run on the GPU. That's an ASIC. It's an ASIC. Yeah. There is also a group of the team lead from TPU left and started his own company called Grok. And they have just published their benchmarks, which are best in class. Any other questions?
Thank you.
Yeah, thank you.
Concluding this session, and we can break for lunch.